Michio Kaku, a prominent physicist and science communicator, has dedicated much of his career to unraveling the mysteries of the universe, often exploring the complex enigma of black holes. These enigmatic cosmic giants, which form from the collapse of massive stars, have fascinated and mystified scientists and the public alike. Black holes possess gravitational fields so strong that not even light can escape them, creating a paradox that has led physicists like Kaku to question what actually lies within these mysterious cosmic entities. Recently, advances in theoretical physics, observational data, and new hypotheses have started to reveal answers that are as astonishing as they are puzzling. In simple terms, a black hole can be imagined as a region of space with a gravitational pull so intense that it warps time and space around it. The boundaries of a black hole are defined by the event horizon, a point beyond which any matter, radiation, or even light cannot escape. Once something crosses this boundary, it is effectively lost to the universe as we know it, hence the popular image of black holes as cosmic vacuum cleaners. However, what's truly inside these entities is still open to speculation and study, and that's where Michio Kaku's insights offer a fresh perspective. Kaku's explanations often begin with a fundamental understanding of general relativity, which describes gravity not as a force but as a distortion of space and time. Einstein's equations predict the existence of black holes, but they also lead to a paradox when attempting to describe what happens inside them. At the core of a black hole is what scientists refer to as a singularity, a point of infinite density where the laws of physics as we know them break down. General relativity doesn't give us a way to describe the singularity accurately, as everything from matter to time is thought to collapse to an infinitely small, infinitely dense point. But this is where Kaku's work takes a different approach. By blending general relativity with quantum mechanics, he introduces the concept of quantum gravity, a theory that could allow us to understand what truly lies within a black hole. According to Kaku, one potential answer may lie in what he calls the quantum fuzz. This idea stems from quantum mechanics, which suggests that particles exist not as distinct points but as probabilities of being in multiple places at once. Kaku theorizes that at the singularity, matter doesn't collapse into an infinitely small point but rather exists in a fuzzy state where quantum effects become dominant. In this quantum fuzz, the extreme gravitational forces and the quantum effects interact in ways that we are only beginning to comprehend. The implication of this theory is that black holes might not lead to a definitive endpoint of matter, but rather to an altered state governed by the strange and unpredictable rules of quantum mechanics. This notion of quantum fuzz also leads to a discussion on the concept of information within black holes. The laws of quantum mechanics state that information, such as the properties and characteristics of particles, cannot be destroyed. However, black holes seem to defy this rule, as anything entering them appears to vanish entirely, leading to what physicists refer to as the information paradox. Hawking radiation, a theoretical phenomenon named after Stephen Hawking, suggests that black holes emit a small amount of radiation over time, causing them to lose mass and eventually disappear. Yet, if a black hole evaporates completely, what happens to the information that fell into it? Kaku, like many physicists, believes that resolving this paradox will bring us closer to understanding the true nature of black holes and what's inside them. A prevailing theory that Kaku discusses is the holographic principle, which suggests that the information within a black hole might be stored on its two-dimensional surface, the event horizon. Imagine, for instance, that the three-dimensional contents of a black hole are encoded on its outer surface, similar to how a hologram holds a three-dimensional image on a two-dimensional surface. This radical concept, supported by advances in string theory, could mean that black holes don't destroy information after all. Rather, they transform it and store it on the event horizon. Kaku argues that if this hypothesis is correct, it would not only resolve the information paradox but also transform our understanding of the universe, as it implies that our own reality could be a kind of hologram where the true information is stored on a distant cosmic boundary. Moreover, Kaku often refers to wormholes and the possibility that black holes could be gateways to other parts of the universe, or even to parallel universes. Based on Einstein's theory of general relativity, wormholes could theoretically connect distant points in space and time. In this scenario, black holes might not be dead ends but rather tunnels, leading to different realms. Kaku has speculated on this idea in his work, explaining that if such wormholes exist, they could provide shortcuts through spacetime. However, these would be inherently unstable, likely collapsing before anything could travel through them. Nonetheless, this concept opens up a fascinating possibility that black holes might be more than cosmic graves. They could be portals to new regions of the universe or even to alternate realities. Another hypothesis gaining traction is that the interior of black holes could lead to what physicists call baby universes. Kaku and other physicists propose that as a black hole collapses, it may give rise to a new universe with its own set of physical laws. Imagine that our universe is just one bubble in a much larger multiverse. Each black hole could spawn a new universe, connected to its parent universe by a singularity. While this idea is still speculative, it aligns with the broader notion that black holes could play a fundamental role in the birth of new universes and might even suggest how our universe originated. Kaku's exploration of black holes also extends to their potential role in the ultimate fate of the universe. Black holes are known to consume stars, planets, and even other black holes. This process of merging and growing creates supermassive black holes, which reside at the centers of galaxies, including our Milky Way. Over eons, black holes could eventually dominate the universe, consuming most of the available matter. This grim scenario leads to what's called the black hole era, a distant future when black holes will be the last remnants of a once vibrant cosmos. However, even black holes aren't eternal. Through Hawking radiation, they lose mass over trillions of years, eventually evaporating completely and leaving behind only faint radiation in an empty, cold universe. Interestingly, Kaku's views on black holes offer a profound philosophical perspective as well. Black holes challenge our understanding of reality, questioning the nature of time, space, and matter. For Kaku, studying black holes isn't just a scientific endeavor. It's a means to explore questions that touch on the very fabric of existence. What does it mean for information to be preserved? What happens to matter and energy in the extreme conditions of a black hole? And what role might black holes play in the cycle of cosmic creation and destruction? These questions push the boundaries of human knowledge and reveal the limits of our understanding, reminding us that, even in the age of advanced technology, some mysteries of the universe remain tantalizingly out of reach. Yet, Kaku remains optimistic. The recent detection of gravitational waves, ripples in spacetime caused by the collision of massive objects like black holes, has opened a new era of astrophysics. These waves provide a unique way to observe black holes, and Kaku believes that they could eventually allow us to see inside them, in a sense, by analyzing the information carried by the waves. Coupled with advancements in quantum computing, artificial intelligence, and space observation technology, Kaku envisions a future where we may finally unlock the secrets hidden within black holes. In recent years, the Event Horizon Telescope project achieved a groundbreaking milestone by capturing the first-ever image of a black hole in the galaxy M87. This iconic image confirmed the existence of the event horizon and provided visual evidence of the intense gravitational pull of black holes. Although it didn't reveal what lies inside, it marked a major step forward in our understanding. For Kaku, this achievement demonstrates that humanity is on the cusp of a new era in astrophysics. With further observations and advancements, we may eventually develop tools sophisticated enough to penetrate the veil of the event horizon and glimpse what lies beyond. Kaku's work and the broader field of theoretical physics remind us that black holes are not just destructive cosmic objects. They represent a frontier, a boundary where science and mystery converge. As we deepen our understanding, we may find that black holes are integral to the structure of the universe, influencing its evolution and possibly holding the keys to other realms beyond our comprehension. Whether as pathways to other universes, cradles for new cosmic realities, or archives of information, black holes are likely to continue to captivate scientists and the public for generations to come. Michio Kaku's explorations invite us to think of black holes not merely as cosmic anomalies, but as profound mysteries that could one day lead to a new understanding of reality itself. Through the lens of quantum mechanics and general relativity, black holes are slowly revealing themselves, piece by piece. And as we edge closer to unraveling these cosmic riddles, we are reminded of the boundless curiosity and determination that drive us to look ever deeper into the vast unknown.